Hello everyone, my name is GizmoCrusher17 and today I have an interesting video for today. I said the day twice, ignore that. Anyhow, I have the explanation for this adder. This adder is the prize of my collection, the prize of my mini computer, and this adder is of my own design. It is not fast, it is by far from efficient, but it does the job. And honestly, that's all I care about for this computer. So if you are following along with this computer tutorial and you want to build this for yourself, then this is the video for you to understand how this adder works so that you are able to better use this computer to its fullest capacity. To start off, I need to explain the level 2 fundamentals of binary. How does binary add? Now, that is a bit of a more complex section of binary. It does have a few more variables, but if you think about it, it does not have as many more variables as we add two numbers together. Now I'm going to go ahead and list down two numbers that we would typically just add in our head, right? I'm going to do 17 plus 17, all right? Now the way that you would add these two numbers together is typically like this, where you have 17 plus 17, just like that. And you would add together these two digits, 7 plus 7, but that would equal 14, correct? Now, if 7 plus 7, which equals 14, then that means there's two numbers in a single number's place, or there's two digits in the ones place, and that's not possible in math. So what you're supposed to do is carry the number. So you take the 1 that was in the tens place, the 1 from the 14, and carry it over to the tens place of our addition. And then we carry the 4 down into our solution. That is the ultimate ones place solution. But now we have to solve for tens place, which is easy. It's 1 plus 1 plus 1, which is 3. So there we go. We just solved this equation. It's 34. That would not be complex if you didn't have to put all the steps into words. But when you had to put the steps from step 1 to step 10, which, by the way, I don't know exactly how many steps, I'm just pulling a number right out of my bum. If you pull all the steps 1 from steps 10 and list them, it will be more complex than it should be. Because you don't exactly think about all the steps by words. You just think, I need to do this, I need to do this, I need to do this. But that's how humans work. Computers, ALUs, and adders, they do things completely differently. They have to go through those steps each and every single time, and they have to think about those steps each and every single time. There is a circuit inside of a computer called a control unit, and it takes programs from what's called a program counter, which is this wall of levers right here. You insert a program, and you throw that into the computer, and the computer will decide what to do with that information, given what commands you give it. So there will be a command that says input data to input B of ALU, input A of ALU, throw it into register B, or register E, or I don't know, any sort of different registers. And it will decide what to do with that information in order to complete a mathematical equation. Let's, for example, go over that same mathematical equation, 17, which is going to be 0, 0, 0, 1, 0, 0, 0, 1. And then we're going to go ahead and add the same number. So 0, 0, oh, I didn't mean to, 0, 0, 0, 1, 0, 0, 0, 1. And that is 17 in binary. So now what does the ALU have to do in order to complete this calculated function? There are two numbers in the ones place. So let's look at this in the numerical place. Tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, okay? That is how we're going to go ahead and look at this. So there are two numbers right now that we need to add together in the ones place. However, we cannot have a 2 in binary in the ones place because the value in the ones place is ultimately 1 and it can't go any higher. In order to go higher, when we add these two numbers together, we have to carry these two ones over tens place, where the value is 2. So that makes sense, right? 1 plus 1 is 2. Very, very easy. All right, so now we go ahead and repeat that process again. So there's 2 ones again in the same place, but there can't be 2 numbers of the same in the same place. It's not physically possible for the binary value. So instead it has to add together and carry. It merges into 1 and carries to the next place to the left, which this right here is a 32nds place in the binary value. So it goes 1, 2, 4, 8, 16, 32, 64, 128, the very last digit right here. And all those numbers, then if we add them together, so 32, which is the ultimate number selected, and 2, 32 plus 2 is 34. So we ultimately get the same answer, but in a different form. Now, this alone is not complex because you don't have to throw numbers into registers to temporarily save them for future calculations. Instead, we're just simply adding 2 numbers together and getting a result. I'm going to go ahead and represent, or not represent, but throw in that exact calculation. So we predicted that it was going to be 0, 0, 1, 0, 0, 0, 1, 0. That was going to be the answer for 17 plus 17. So that's 2 plus 32, which is 34. Let's go ahead and add 17 and 17 together. Now this adder, because of the way it's configured to the size of the computer, I have the inputs and outputs on one side of the adder. That way there's no extremely complex inputs and outputs on both sides. This can be just laid against the back of, or the side, or wherever of the computer. But because that's the way it is, we have to read the adder like this, so you can read from the right to the left. But that's not really an issue. Let's go ahead and throw in 17. That's going to be a 1, 0, 0, 0, 1, and then again 1, 0, 0, 0, 1. If you look over here, 0, 1, 0, 0, 0, 1, 0, 0. 0, 1, 0, 0, 0, 1, 0, 0. The exact same solution. So I just explained how 2 numbers in binary would add. But then you think, well, what's the point of an adder? If you have to add the ultimate solution anyway, you have to add the last 2 fragments or last several fragments of the number together in order to get the actual solution. And that would make sense because, for example, 127, which is one value away from being 128, is, I did not mean to, I'm messing things up. 1 second, I'm messing things up badly. There we go. 127, which is one number, or one value away from being 128, you have to add 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64, and you have to add all these numbers together to get 127. So what's the point if, like, for example, this is the output of one of your mathematical problems, is 127 is your output. You have to add all these numbers together to get the ultimate output. Well, that's where we have other contraptions that do that work for us, and those contraptions are decoders. Now, unfortunately, this decoder is not, what's the word I'm looking for? Appropriate for this adder. Because if you were to input binary value 10 into this adder, which is 0, 1, 0, 1, then it would come out as a dash or an error because there's no program such as 10, because there can't be 2 tens or 2 numbers in the tens place. Nifty, right? So if that is the way that this is, this will not really work for that. But we have another contraption called an encoder. Now the encoder takes this binary value and throws it into a value that this decoder can read. It turns an 8-bit value and it cuts it in half, and the first 4 bits is changed into, I do believe, is called octal format, octal binary format. I'm not 100% sold that's exactly what it's called. I could be completely wrong, and I most likely will get blasted in the comment section that it's wrong. I might show if I'm wrong or not. But it takes this value and changes it into something that can be used in this decoder. So instead of giving an output that says 0101 as 10, the value instead changes, and I actually have a value list over here. So this right here, 1001 in the pink, blue, and white, that is 9. 10, which is right here, 0101, as I mentioned earlier, is the value 10. That value has to be changed into this format in order for another segment of the display to pick up the slack and show the alternate solution. Now there's clearly ways to do this where you don't have to have these bigger contraptions that have to encode and decode and roundabout and all this weird stuff. There's ways you can do that. I find it a bit more entertaining and challenging to have this limited space and still be able to fit this much stuff. This just means I can make it smaller by being more efficient. But anyway, that's off topic. So these contraptions have the job of taking the output from our ALU, our ALU ultimately, and turning it into something that could be used in the display. So display cannot, outright, you can't plug and play with it, you have to add other components. A good example of an adder taking an output and changing it into a 7-segment output is this right here. Now this is an encoder. This is ROM, basically. It is what is underneath that display, that entire green circuit. This is what's underneath that display. And by the way, this is my 128-bit calculator. And it's actually pretty awesome. I haven't finished it quite yet, but it's close. So this calculator can calculate the 120-bit numbers. So all of this is that green circuit underneath that display. This is the decoder. That's the encoder. This is the decoder. See, the roles for each of those circuits has changed. That decoder for that display has now been turned into an encoder. And this is the decoder. This takes the output from our encoder into a format that the display can give an appropriate output that you can read without having to do a whole bunch of hieroglyphics and stuff like that. Some ridiculous bull crap. That is the job of this circuit right here. The real computing, the real calculating, happens in that small itty-bitty little area. The language processing happens here. And language processing usually is the biggest part of a computer. It's where everything has to happen in order for you to get an accurate output. Alright, so this will be another good example of decoding. Now this machine right here is supposed to have its own dedicated GPU. And it might seem completely humongous and ridiculous to have it this size. In fact, this is actually a failed experiment due to several different glitches that Bedrock has, including this dropper hopper T-flip-flop. But this system right here is a good example of using a encoder and decoder to make an appropriate image. Now this might seem a little bit off topic, but this brings across my point perfectly. If you're to throw that information from the adder into this computer with just the numbers, just the binary value as is, it would probably come out the same as binary value, except it would all jumble up in one line. But we have extra components in the system that decode it for us. So more on this concept probably later on in another video, and why I didn't choose to go along with it. This system right here is actually supposed to be a you can select each and every individual pixel, 1 by 1 pixel, so a single block. It is pretty monstrous, but it was my own design, and honestly I couldn't think of anything else better. But that'll be another video. But this kind of brings across the encoding and decoding part of calculating functions. Alright, so now it's time for the next half of our explanation for this adder. Why I'm using this adder. As I previously explained, all the inputs and outputs for this adder are on one side of it. The back is actually where the carry is. So I can literally just go ahead and take this adder and throw the back of it towards the edge of whatever I'm using, and just pull all the information from one side. It makes things a lot simpler and easier to construct. It also means that you can make much more compact contraptions. These adders right here, this is the evolution of this adder, this is the ultimate end. These adders right here are what I had to develop. This is Benny's Cube design of a 1-bit full adder. Now this adder is very efficient, it is very fast, and I love Benny's Cube designs. A lot of his videos, it might seem bad to say this, they are outdated. They're several years old. But because they're outdated, they work very well for Bedrock Edition, especially for a good 80% of his contraptions. But this is one that works on every edition, this adder. Now, this adder is not space efficient, and I think I do believe I just said that earlier. If I didn't, I'm just repeating myself. If I did, I'm just repeating myself. But this right here is not space efficient. In fact, 32% of the blocks in this contraption are not used. That is unacceptable for my contraption, for my computer. Now, not only is does this adder take up less space ultimately, but it's also more space efficient. In fact, only 12 blocks out of the 95, I do believe. What are the numbers? So here it is right here. This is 8% better than the traditional adder, and it uses 21 blocks less than this right here. So 21 blocks it's 21 blocks smaller in mass compared to this adder right here per bit. So if you were to line this up in a huge array, which I actually have a full design of it in my calculator, if you were to line this all up in an array, it would take up more space than this would. This takes up a whole bunch less space, and there's only 12 blocks out of, I think, the 95 blocks here that are not used. It is 48%. Alright, so now you know why I chose it. Space efficiency, size, and ease of access. Now, what are the downsides to using this calculator? Well, there's a few things you need to know about this calculator, sorry. There's a few things you need to know about this adder. This adder is slow. Very, very slow. It is, I think, Benny's Cube's design for an adder right here could finish a calculation 10 times over, while this does the same exact thing once. In fact, let me go ahead and demonstrate that real quick for you. So I have the simplest of solutions, calculating, and it's putting 1 in all of our inputs, which means we have a total output of 127. Now, adding 1 to all these digits will make this carry, and that 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 carry, all the way to 128, because 127 plus 1 is 128. Let's go ahead and look at that. Wow, fast, right? And there's no cuts in that. That's super, super, super fast. This is also a Benny's Cube design. And I would have used this, but I'm scared away by space efficiency and the fact that it's vertical instead of horizontal, which is what I want. Another reason why I chose this adder from others. But let's look at how slow this is. It's slow. It is very, very slow. But speed is not my forte with this computer. In fact, it's the complete opposite. I want this machine to take its time. The places where it's impressive is its size. So I guess you can say this computer is compensating for something. It's compensating for speed by its size. Okay, so now after showing this, I might scare away a majority of viewers for this computer. But do not fret, the tutorial for how to make the adder and ALU combined will be extremely detailed, and it will be even a two-part video. The multiplexer will be on its own video. This entire area is a lot more complex than people give it, or not, more complex, a lot more simple than people get credit for. But this is a good way of showing how it interfaces with the components. So this right here is the ALU, or well, the logic. The entire system is the ALU, but this is the logic part of the ALU. This right here is the AND gate, do you believe? Yes, the AND gate. This right here is the OR gate. And this coming up from the back right here is the output from the first XOR gate in the adder. So we have all of our logic functions, our logic gates for this ALU, and we also have our arithmetic. In fact, a good example of this machine working on full speed is going to be this. I'm going to go ahead and select adder, which apparently there's something in it right now. Let me go ahead and clear it out. There we go. And I'm going to go ahead and input the number 7 plus 7 again, so you know that it does work properly. Input it, register A. Okay, straight output, register B. And we should have, this is 7 plus 7, so it should be 14. So this is 8 plus 4 plus 2. 8 plus 4 is 12, plus 2 is 14. So there you go. We now have our final output. So as you can see, the adder still works. I will be going over the rest of the function of the ALU, but this is just to show how it interfaces with the computer and the reasons why I used it. When I designed this computer, I made sure the entire bottom section right here was the CPU, and that's the case. We have our adder, our adder, our logic, our multiplexer, our registers, and our inputs all in the ALU all in the CPU right here. And that's all I need. This entire area has been planned out to perfection. That being said though, if you are not interested in building this computer, and I'm talking about the world's smallest Redstone 8-bit computer, then don't build this. If you're not interested in it, then don't build it, because this adder is not useful for any other contraption other than this computer. That does mean that this is kind of a useless contraption, considering that, for one, it works on a quote-unquote bug for Bedrock Edition. It has the piston torch bug. I call it a feature, but to each their own. That could be taken away at any point in time. And it also only works for one contraption. I mean, you could clearly use this for something else or anything. You could use this for whatever computer, but I don't recommend it. There's far better and far faster options out there. For example, Benny's Cubes design, which I have right behind me, peeking up behind this adder right here, this monstrosity. So, if you're not interested in building this computer, then do not build this adder. You can go ahead and skip the next video, even though it's interesting to watch. Maybe if you want to watch it to learn how it works, how everything connects, then go ahead by then. But again, I don't recommend building this for anything else other than the 24x24 cube computer. Self-sabotaging aside, that is it for today's video. If you guys enjoyed it and you would like to learn and see more of my content, then go ahead and leave a like and subscribe if you would like to see more content. Ring that bell, because this computer is only to get more and more bonkers and just crazy in general. It's going to be a really interesting contraption, and I don't want anyone to miss it out. It's going to be a lot of fun. Anyways, guys, my name was GizmoCrusher17, and I'm out.